entertaining. So the history of this work, which is in collaboration with my colleague and my academic brother, Mohammad Ali Zadeh, who is at MIT. This is primarily work of 3 graduate students, Abdullah, Puya, and Arash, in collaboration with Anish. This is the preprint. Now, the way it started is 2020 December, which is in the middle of pandemic. For my brother-in-law's wedding, I was in India, in Delhi, in a hotel, and I was stuck there. And Mohammed and I were supposed to write a paragraph for one of those big NSF grants. And it realized that neither he or I had done our work. So he called me saying, let's write a paragraph together. And I was saying we should do something about causal inference. And he was saying we should do something about network systems. And that beautifully led to this collaboration and lots of interesting projects that have come out of this. Of course, the grant did not get funded, but it did the work. So that's the most important reason why we should write proposals, just paragraphs. All right, so with that, what I'm going to do is I'm going to briefly explain one of the setups in which we are trying to build network simulator for simulating what would happen to the outcomes of network communication network quantities in a trace-driven manner, and I'll make it precise what it means. And the system that comes out of it is Causalsim. It's the work is both methodical and there is a lots of empirical work. So I will try to do justice to both to the extent I can in the time I have. All right. So here is a simple question. All of us see and consume video content online these days in all forms, be it Netflix, be it Zoom or anything else. At the end of the day, there is some video player that you have on your device that's constantly talking to a server sitting in cloud and asking it to send it data to play the next part of the video. Okay, and on one hand, ideally, the server wants to get, your player wants to get as much data as possible so that it gives you as high quality experience as possible. On the other hand, if network conditions are poor, by the time the data that you asked arrives, it might be too late and you might have this jittery experience. So how do you balance this jitter on one hand?
You should mute.
Okay.
Mute, can you hear us? Mute.
Thank you. So by the time the data comes back to your player, you want to make sure that you have enough playback time available. Okay, so it's always a balance between this. And the whole goal of a good ABR protocol is to make sure that it constantly keeps adapting to this situation. All right, so just to make it a little bit more precise, roughly speaking, the way this algorithm or this protocol works is as follows. There is some notion of, let's say, decision step T. At that time, you have some amount of time worth of video content is already available. Okay, so this is the amount of time you can go without having any more data. So that's good. Higher it is, you can be more aggressive and ask for more data for the or higher quality things. Lower it is, you should be in trouble because soon you will start experiencing the jittery things. So at some level, your protocol now chooses some rate. Rate determines the how much amount of data that will come back to you from the server. Okay. And then there's a network condition unknown, of course, hopefully not changing drastically, but that will determine some effective throughput. So this is the amount of time it will take for that data that you asked for it to reach. You had this much of buffer that's gone. Okay. And of course, each decision cycle, roughly speaking, corresponds to T amounts of time worth of video play. Okay, so this is how roughly the dynamics evolves. And of course, if it took too long and if you ran out, of course you ran out. Any questions?
CT is dividing the S or the
yeah, so CT is my rate.
Yeah.
So ST is the number of bits I want, and then I divide it by CT. So that will be the amount of time it took me to get that content from the server. And by the time that much amount of time I used my existing buffer to play. So now my buffer has shrunk, but then it increased once it reached. And if you're a person, if you have seen queuing, this is like a queue. So far, so good. And again, question is, what is the best protocol? And if you think from reinforcement learning perspective, this is one way to think about this is a nice reinforcement learning problem, but with partial observation. I'll hint on that in a bit. All right, so if one has to ask this question, and if you're at causal inference workshop, you'll say, well, just run randomized control trial. So you have 5 different protocols that you really think are great candidate. And then now you go and deploy them in wild. Okay, and every time you have to sort of run a video stream, you choose one of them at random across people, across time and all that, and then sort of see the performance and then based on that decide. Okay. This sounds daunting, challenging. Turns out there's a group at Stanford did go ahead and do it. So these are the Yan, Iyer, Zhu, Foldy, Hong, Zhang, Levis, and Keith Weinstein. They did this experiment from August 2020 till May 2021. It was a collection of client server setup across the country in different data centers and a cloud environment. And then through that, they've collected this data set called Puffer. Okay, they ran 5 ABI protocols. It corresponds roughly to 4 years worth of video. So if you got that video and you started watching today without blinking your eyes forever, then it'll take 4 years. So it's a reasonable amount. And they measured all sorts of things. These are just a few things I'm reporting. Okay, so it's a very, very nice experiment. It still continues to go on. We're going to sort of use this data set. And that's it. All right, so what's the question? Well, now I have my own protocol. That's called Fabulous ABR. Okay, now I want to try it. I want to compare it with those 5 things. So one option is I can again go back and run for 1.5 years and see what happens. And maybe now sort of instead of 5, it's 6. So maybe my time should increase by 6 by 5. Okay, and so on. So clearly this is expensive. So maybe alternative would be to say, well, why not try to use the same protocol, but on the traces that you have collected. Okay, so I have collected traces under 5 protocols historically in the Puffer data set. I'll go back and I will run effectively now those or simulate those traces under the sequence of actions that I will take as my algorithm. Now, of course, there are a few challenges. So let's see what are those challenges. Now, before I sort of fully address the challenges, here are sort of few approaches that I'm going to put out. One is naturally the obvious approach is say, let's do supervised learning. Well, I observed historical data. I know every aspect of dynamics that I could observe. So from there, let me come up with a model of dynamics and then learn it, supervise learn it. And then, so we would use a nice neural network for that. Another is, since I had laid out this dynamics clearly for you, and I'm an expert, I'm just going to use this. That is for every time step t, I knew what was the realized throughput, what was the action I had taken, and that's how buffer changed. If I changed my action, of course, throughput will remain the same, and I will sort of now evolve my buffer differently. That's how. And then the third one, which is the method I want to discuss, I'll do that in a bit. Okay. Now, one question is sort of when you have a data set like this, okay, let me sort of pause this for a second. If you have a setup like this, question is that how do we evaluate? How do we evaluate that whatever method we have is doing good or bad? Because I don't have the counterfactual, right? Remember, I had 5 protocols, and each protocol was assigned one of the streams to play at random. So if you believe in RCT, And effectively, what it says is that the type of network characteristics that each of the protocol will see in a distribution sense should be the same. So maybe we should look for certain distributional characteristics of protocol and then see if it does well. Putting it other way, if here is what we are going to do. So we have 5 policies. Okay. Let's say one of the policy in the data that I have, I will call it my fabulous ABR policy that I want to simulate, and I'm going to take all of its data out. Yeah.
Missing something about the application. So
yes.
So imagine I measured the C-hat sequence.
And you have measured it actually.
So imagine I have understood the distribution of sequences of C-hats.
Yes.
Is that enough information to evaluate anything I want or not? Is there a feedback loop between what the ABR protocol I'm using and the C-hat that I'm seeing? Or is it literally like the distribution?
So in this case, it's something in between, but that's exactly the problem. And that's where one needs more than supervised learning. So if C-hat was not impacted in some sense by my action, then this is it. But in reality, it does get impacted. And I think that's basically the issue. That is, so the question is that, what is that and how does one account for that? Thank you. Perfect question. Please feel free to stop me. Okay, so so what are we going to do? There is one policy whose data we're going to just withhold. Okay, there is another policy. Let's call it target. In this data set, let's call it BBA. It's one policy. So I've got a bunch of traces under it. I'm going to use them as a source. So what I'm going to do is I'm going to take these traces and over which I'm going to run my policy and see what the outcomes look like. Okay, and then the policy would be supervised learning, the expert simulator, and then causal sim I'll describe soon. And then what I will do is I will try to measure performance in terms of distribution of buffer occupancy. So distribution of buffer occupancy under the simulated policy that I have and the actual data that I have. And hopefully they should match. They should match if my simulation is good. If my simulation is not good, they won't match. So here is a result in a nutshell. So this is CDF, okay, and this is buffer occupancy in seconds. The withheld data set, which is this, which is actually this pink dashed line. Okay. The training data set, or rather the data set on from which we altered, is this black dashed line. And as you can see, black dash and pink are different, which means these are sort of two different policy outcomes, understandably. And what you really ideally want is, if good simulator you have, it would causally transport it from this to that. Okay. The green method that we have, Causalsim, actually does that, at least visually does that well here. The blue one is the expert sim, and the red one is the supervised learning. And so what this shows is that these guys are trying to simulate the training or source policy that you already had, versus Causalsim somehow figures out how to transport it. Okay, so in a nutshell, it has to correct for something that's hidden, something that is confounded there. Okay, and that's basically all that's happening behind the scenes. Right, so what is that confounder? So the confounder actually is the true network throughput. So imagine that I asked my network to send me data at 1 kilobits per second, and network send me the data at 1 kilobits per second. But maybe network capacity at that time was 1 megabit per second. Just because I saw it at 1 kilobits per second doesn't mean it's actually 1 kilobits per second. And that's basically what's happening. That is, when you see the observed throughput, you don't know what is the real capacity. And if you could, then potentially you would be able to figure that out. And this is exactly what's happening, that BBA, the observed throughput is like this. Under Fab ABR, because we have the data, the observed throughput look like this. Now, observed throughput are not the network latent network condition, right? Network condition, if good RCT is done, there should be same. Of course, we don't know that, but observed are different because the policies are different. All right, so now that I've told you at least the issue in a nutshell, let's try to sort of model it, and let's say sort of how this model will help us come up with a solution. So here's a simple dynamical systems model that we'll use. So at each time step, we take an action, and action in this context is deciding how much data to obtain for this each chunk. This is my observed buffer occupancy, my observed state. My action impacts my realized throughput, because if I ask for 1 kilobit, it's going to give me 1 kilobit. If I ask for more, it will give me more. And there's a latent network capacity, which I could realize. So these two things determine what my observed throughput is. And observed throughput, along with my action and along with my previous buffer occupancy, determines my new buffer occupancy. So this is my model in a nutshell. Any questions? And again, other than gray, everything is observed. Now, in the spirit of SCMs, basically, one way to represent this dynamics is to say that, well, there is some function of action and this latent state, which determines this, my intermediate mediator, which I observe. I don't observe U, but I observe A. I don't know the function. And then I've got some other function that maps my previous state, this mediator, and then the action to give me the next state. Yeah.
All right, so this is happening at some instant in time.
Yes.
Now the latent variables across time
Are changing.
They're changing.
Yeah.
And
So UT plus one, UT plus one. I'm going to assume that they're exogenous.
And so they may also be confounded with each other. So you're assuming any independence between them, or?
Good. So I'm assuming that these are given to me because I'm, as one ABR decision maker, I'm a drop in an ocean. So my making decision is not going to change my network's condition, but it will definitely impact my realized throughput.
So they may be correlated amongst themselves as they like, but they're a sync for you.
Yeah. So I'm really interested in saying that let me go back to the same that instance, assuming the same network capacity available to me, and let me change these things.
But there's no stationarity, so there's no.
I'm just giving you this. But this is an assumption. Okay. All right, and so, and just setting the question in the context of the data we had. So we've got n trajectories collected over K protocols under RCT setting. A trajectory I, let's say, some length of steps. For each time step, we observe these things. These are my latent things. Now, simulation would say that instead of these sequence of actions, I've got some other sequence of actions, starting with the original buffer occupancy, let's call it O0. Now sequentially simulate it so that I can get O twiddles. And while I get O twiddles, of course, in the intermediate setting, I will get M twiddles too. Yeah, so this was the M, this was my buffer, this was my action, and this was my network, latent network capacity.
And you made a comment earlier about the that policy could actually.
So in a sense, this is my unobserved confounder, which is.
Policy doesn't affect
So at this stage, I'm saying actions are just given to me. And I just want to now change the actions because I got this model. Okay. So now let's see sort of how one would go about this. So at least there are two functions, right? There's the f and g. Well, these things I observe, and let's assume that I have observed things enough, and there's enough diversity so that I can do supervised learning. So maybe I'll be able to learn g. Okay, so that's not a problem. But now I need to know m twiddle. Well, to know m twiddle, I need to know f. So m twiddle is function of a and u. I don't know u. I don't know f. So the problem is m twiddle. If I knew somehow m twiddle, then I'm done, right? Because then I will take the m twiddle. I will learn g. I'll just plug it in. I'll do this sequentially, and I'm done. Okay. So really, the whole problem is m twiddle. Okay with that? So, okay, so let's write m as this. It's a function of two variables. If function is nice, let's say nice continuous function, Lipschitz, and let's say that the actions and confounders themselves in some latent representation, if not actual, they're coming from some compact domain, then they would have some kind of singular value decomposition, which would effectively look low rank. Okay. Let me posit this. Okay. If you don't like it, let's say this is, I'm positing this, and we'll verify for the data and all that. But if we believe into this, then one way to look at my problem is this. I've got those actions on rows. I've got columns which are my unknown u's. Okay. And the entries are my m's. And this m is some factor associated with action and some factor associated with the confounders, and then just inner product of them. So maybe effectively I've got now to do m twiddle, I need to do low rank matrix completion potentially. So let's see how that looks like. So let me take a super simple example. Let's say I've got just two actions. Okay. And now I've got number of confounders, and as Leo correctly pointed out, for every trajectory and every time instance, there is a separate u. So effectively, I'm stacking up all of those things, lots of them. Okay, so this is like really, really, really wide matrix. Okay, and the data would look something like this, right? Because there are, I'm just without loss of generality, I'll put some of them I would observe in first row, and exactly for the other columns, I would observe the second row. And I want to find this out. And let's assume, to keep things super simple, it's a rank 1 matrix. But still, I can't solve this, right? So something got to give. There's something that we have not utilized that we utilize to solve this problem. And okay, I got a few more, 3 more minutes maybe. Sure. No, it's the end of the day. It's a bad karma.
Open problems at some point.
Open problem, but bad karma. Okay, so here's the thing. We have not utilized that this data came from randomized control trial. If it came from a randomized control trial, and okay, this is not exactly, you don't really think of this as a policies in that setting, but let's think of simply its actions. Okay, so then the distribution of confounders that got action 1 should be similar to distribution of confounders that got action 2. In particular, the first moment of the latent factors of this should be same as the first moment of latent factors here, which means that I can take average of this green, average of these greens, take the ratios. That should give the ratios of the factors associated with these 2 things for rank 1. So that solves my rank 1 problem. If I have a higher rank problem, I need a little bit more. I need more measurements. So one way to do that more measurement, just stack it up. So then it will look like a tensor. Okay, you would need that the measurement dimension is higher than the CP rank of the tensor. You will need the randomized assignment. You would need some coverage so that you can solve appropriate linear equations. But you do that and you'll be able to solve this problem precisely. Now, of course, if you're going to build a system, you're not going to do this, right? So what you'll do instead is something like this. Okay, so there is a discriminator that you will use to make sure that you impose the fact that you know from randomized control trial that confounders that you will find across trajectories and time steps have similar distribution across policies. There is a factorization, and then there's a function that you learn which takes these things to estimate your next step. Okay. And here you would have the quadratic loss we used there. Here we are using the typical discrimination loss coming from the relative entropy. Okay. Coming to the question of ABR, does it have low rank? Now, see, since we don't have counterfactuals, I cannot evaluate the rank. Mohammed and his group have been working on this question for close to more than 5 years now. It started with this beautiful work here. Pensive, actually, it's pretty actively utilized out there in practice. And that was evaluated based on a trace-driven expert simulator that built. And for that simulator, we do this proper look at the right slices and then sort of do the evaluation. It turns out to be at least 99% of energy is captured by top two components. Let's see, I've got maybe 2 minutes. Okay. Now you can sort of use this simulator. So take the data simulator. On simulator, you can train the policies and all that. And short of the long is that it does actually help you improve quite a bit in terms of effective quality of service or how, as a viewer, you find it. There are other problems like load balancing. So if any reasonable system that's designed right now will have a good load balancer. Load balancer will have jobs coming and jobs assigning to servers. You don't know what are the service rates. You don't know what are the job sizes. Again, put it through the similar setting. The effective quantity of interest, which is time it takes for a job to finish on a server, is actually rank 1 matrix there. And similar thing that happens there as well. There you could sort of actually have an interpretation of latent factors captured by the system. They would actually should correspond to job size, and they do. All right, so ending now in the last 30 seconds. See here, what we have done is we've utilized, among other structural assumptions that many of the works in this in the broadly panel data setting folks have utilized as the low rank tensor structure, is this structure induced or property or invariance induced by randomized control trials. And now if I look at that, and so if one goes back to the traditional population level randomized control trial where there's an individual who is giving one specific treatment, and I've observed a bunch of measurements for that individual. I only observed that individual under one intervention. But if this observational tensor or matrix had a low rank, then with this invariance, potentially I would be able to do individual level treatment effect evaluation. And I think that's something really exciting. All right, with that, let me stop. Thank you. Yeah.
Load balancing, what was the randomized control trial experiment?
So again, for load balancing, again, in a very similar manner, you have sort of different policies. different policies determine, given the incoming jobs, which servers they're assigned to based on the state of the network. And then every time a job comes, you randomly decide which policy you're going to use, for example, or you run the whole trace under one of the policies, but at random.
Distributional invariance kind of come into the conditions you need for the tensor estimation? Like, is it relate to, because of distributional invariance, you can model the observation noise the space, or?
So actually, in all of this discussion, I ignored the observational noise, but even to just learn the latent factors themselves, I will need, let's say I will need to match the moments of the underlying latent factors across different actions, so that I can solve. I'll generate enough, let's say, system of linear equations, so to speak, so that I can solve them. Thank you.
There should be refreshments waiting for us outside, and then